with MIA Microflight, and this is my MIA Blink Core XY 3D printer. It's an unconventional design by means of the location of the X and Y motors here. You will not see this on any Core XY typical machines. This is the first one, I believe. I searched high and low on the internet to see if I could find a similar machine with the motors in symmetry that you see here, but they're not. All of the machines that are Core XY have the motors at the corners there, and that's how everybody builds the Core XY machines. The reason I decided to make my machine or design my machine this way with the motors opposite to each other, it was to, first of all, I like symmetry in all designs, and that location for the motors, the typical Core XY, the way people build Core XYs, typical Core XY approach, was bothering me. I didn't like the motors at the corners there, and I wanted to make use of the full area here, inside area of the frame. And so I set out to do this setup here. It was a little bit tricky because I had to do some quite a bit of thinking, a little bit outside the box, and I know I'm kind of giving myself kudos for this, but I'm very proud of this particular design, because there are no designs, like I said, out there that are similar to this one or the same. And so I had to do quite a bit of thinking how I was going to rearrange the motors for the Z-axis also, which are in line with the X and Y. There are two motors that operate the Z-axis, and those are sitting right underneath, kind of hidden away underneath the X and Y motors that drive the Core XY assembly here. Now this whole assembly rises as opposed to the table rising, and that's another feature that is very unique of this MIA Blink 3D printer. I didn't want to have a cube for a box. I did an earlier design that follows that particular design mentality, and although it's just another Core XY, I wanted this to be totally different from that design, and so I ended up doing it this way, where these are my towers that allow the complete XY frame to rise instead of having this fixed at the top and having the table rise. And so in this setup right here, what you have is the complete XY, Core XY assembly rising little by little. And I wanted to keep the table as steady as possible, fixed to the table. Now I don't have a table right now that is attached to this Core XY, but the idea when I designed this was to have a base, a solid base, very similar to the Anycubic i3 Megas. They have a solid enclosure that encloses all the electronics and the power supply. It's all in a nice little base, and then on top of that base they have the table. But on that type of machine, you have the table that is on your typical y-axis that goes back and forth. And so with the Core XY, you eliminate that by having the X and Y on the assembly here. But on this particular one, you have not only that, but you also have this rising, and you have the table steady. The table is not moving as I think it should be done. The other thought process that came into mind when I did this machine was I felt that when you write on a piece of paper, your paper is stable fixed on the table, and your hand and the pencil, the tool, is doing the operation of moving in all kinds of directions. It's going up and down, racing up and down, and it's also going in an X and Y directions. And so that was the mentality that I wanted to implement into a 3D printer. I wanted to keep the base solid. It's like your white piece of paper would be on a table. As you're writing, your hand is the one. The tool is doing the lifting and positioning over that steady surface of the piece of paper. And so that's the mentality also that I had, when I did this machine here. Now, this machine, as all machines, they have pros and cons. And the pro with this machine is that I can keep all the X and Y and Z on the same assembly here, as this is rising up and down. But also it has a limit because of this bridge here that you can only go so far here, as most machines do. As if you look at a typical 3D printer, they have a bridge on top, that have to have a bridge, to support the towers on the side, and so that bridge limits the height of the print. And so on this one, the same thing happens, except that on this one it's a little more prominent because you have the bolt and tube cable that's connected to the, I don't have the feeder stepper motor on this machine yet, or the spool, but the feeder is supposed to go on top here in center with the whole system here to maintain the symmetry that I'm talking about here. And I like, my bolt and tube to be in the center, and I also like the feeder with the stepper motor to be in the center. Many people call that feeder motor the extruder. It's not an extruder. It's just misinterpreted as an extruder. This is what's doing the extrusion here, because this is the hot end that is extruding the molten the filament, the plastic, and extruding it into a string of molted or melted plastic. So that's the extruder. The feeder should be called a feeder because that's the filament feeder. That's the one that's feeding the filament into the extruder. So to me, that stepper is called, to me the stepper is the feeder, not the extruder. So that one is going to go here, and it has the bolt and tube directly underneath here. And so as this is traveling back and forth, and as this is rising, this has to have a certain amount of distance here to allow a natural curvature of the bolt and tube without kinking it. And so this machine is limited also by that distance, just like on any other 3D printer that has a bridge, like a regular, let's say an Ender 3 or a Creality CR10 or even a i3 Mega. They all have bridges and they all have limits. Of course, those machines, you can increase the towers and you have more room, to print the higher parts. But for the parts that I do, this machine is not designed to print vases or tall structures. It's designed for speed and precision in printing average size parts. Most of the parts that I print are mainly for my models, and so I designed this machine, to print parts no bigger than 150 millimeters in height. So this machine can go up to 200 millimeters comfortably without having issues, with the bolt and tube kinking, as I mentioned. But I rarely print beyond 4 inches, which is about 100 millimeters in height. So, and this machine can comfortably do that and more. So I wanted to point those things out. The filament spool will probably be on top of here. I designed this tower. I sketched it out, but I haven't completed that yet in the CAD model, so that's still up in the air. The control system is totally isolated from the machine. There are no power supplies, there are no control boards, there are no screens that are part of this machine, because I wanted to keep this as clean as you see it here. And so all that is going to be on a separate unit, and all these cables that come from the motors, from the hot end, from the fans, hotbed, are going to be on the side of the machine, and they're going to have the proper connectors so that I can connect the control system, which also is the power system, to the machine on the side there. So you won't be able to see that. It'll keep the machine clean and modular. I can take this machine, I just simply unplug it, and I can move it away and reuse the power system with the control system on some other machine that has a similar architecture and setup. And so this is my MIA Blink 3D printer with the unconventional X and Y stepper motors as you see them here. You will not see machines like this, and I guarantee you, if you search today high and low on the internet, you're not going to find machines. I tried for a good month. I've been looking at to see who's been doing this. I've had this machine, the concept, for about a couple of weeks now, after I did my first cube type Core XY machine. It's not the first machines that I built. I built CNC machines before. I built 3D printers before, but not of a Core XY configuration, especially this one right here. And so this is my own conception here from ground up. And as I said, you're not going to find a machine that has these motors here like spread out like that, nice and out of the way, clean in my opinion. And it's very different than any of the other Core XY machines that you typically see online. So this is Mario with MIA Microflight. Once again, oh, by the way, this is not connected here because I bought this plate. I thought it came with already set up and ready to connect, but I have to install the thermistors and the LEDs on this plate. Not a big issue. I just need to find the time to do that and to properly attach this to the base here, which also is composed of aluminum extrusions. I should talk a little bit about the extrusions because that's also unique about this machine. Yeah, let me point that out. I am waiting for more extrusions. Unfortunately, I bought all the extrusions the company had to do this machine here, and they only had 3 left, 3 sets of 4 left, and so I'm waiting for those to come in. I hope I hope they manufacture more of these extrusions because, at least to me, they're very useful, and I'm pretty sure they are useful to a lot other people, for small projects like this that don't require the heavier, massive aluminum extrusions people typically use on these machines. One of the things that I was trying to stay away is from brute power. You have probably heard me say this in many videos, especially with my microlights and ultralights airplanes, radio control airplanes that I design, and pretty much anything that I design, even my man-carrying helicopter that I designed, which is in stages right now, that I have not shown, is driven by efficient power, meaning it doesn't have all these contraptions and it's not driven, therefore it's not driven by brute power. As most people tend to build things that are so heavy and then they have to use brute power, there's no efficiency benefit in that respect. However, if you design something strong, rigid, but lightweight, using a little thought, more thought into the structure, the architecture of that, you don't need massive components to arrive at a very lightweight assembly. Look at the bridges, the way bridges are made. They're very skinny rods and in the triangular configuration. And so you can achieve pretty much a bridge that is holding a lot of weight. And so that is my approach when I do these things. Is I don't like to use really heavy components. So having said that, I went online and I started looking for extrusions to see if I can find the smallest extrusion that I could find, and I ended up finding these 10 millimeter square extrusions. They're just like your 2020 extrusion that people use, typically for building machines. That are sold, with most 3D printers, desktop 3D printers these days. So I found this 10 millimeter extrusion. I was a little bit uneasy when I saw this via Amazon, just looking at the photos, and I was like, maybe it's a little bit too thin for what I'm trying to do, but let's see what they look like. So I ended up buying one set, and when I got the set, I was sold. I was like, wow, this is really cool. Miniature extrusions. Let me go back and go buy some more. So I ended up buying more to complete a machine. At that time, I was going to rebuild my typical cube style Core XY, and so when I got the extrusions, I started rethinking the machine, and I go, wow, I can come up with something very, very cool with these extrusions, and something a little bit different than what I've seen out there. And so I redesigned the machine on CAD. I must have had about 9 different configurations, which is easy to do in CAD because all you do is copy and paste, and modify it, keep modifying the different layouts, and you end up with that's how you end up with a refined machine without having to actually build the parts. But I like to build the parts because they give you a more tangible way to see where you went wrong, where you could adjust here and there, and where you need to tweak things. And so this is the way I came up with this machine. And so these 10 millimeter extrusions have been working beautifully here. I did have to make these parts a little bit longer because these extrusions are all 300 millimeters. The other thing I didn't want to do is I didn't want to drill through these extrusions, as some people tend to, just go drill, oh, no problem, I'll just build a frame, but I'll drill holes all over the place. I don't like doing that. I don't even do that on my RC radio control ultralights. People also tend to do that. They tend to drill right through the walls of the tubing, which make it weak, in that respect. But in here you can get away because it's an extrusion. It's it's a little more rigid. But I don't like drilling through this. So these come pre-drilled with a 3 millimeter thread internal thread on the ends. So you can, and they sell these little blocks, I think they're aluminum blocks that you can attach at the corners here, so you can insert a screw that way and that way. And that way you lock up the the frame that way with these little square ends that are also perforated to allow the screws to go in and attach to the corner here. So I bought those. I bought some hardware here. There's some sliders here that go fit inside the tracks inside here where you can attach things to that. But I decided not to use any of that stuff, and decided to just make my own corners with the with kind of a similar attachment point here. And that's why you see these holes here are a little bit larger on the sides, because these have a screw inside this hole here that attaches on a small on about 4 millimeter wall thickness. You don't see the wall thickness because it's embedded in the part before the extrusion. So it locks the extrusion that way, and it locks the extrusion that way, and that's how you or I was able to make this frame here. The same thing at the bottom, you know. So this is very solid, very solid frame here. It's not twisting, it's not shifting, it's not going anywhere. So that's the way I did that machine. The other thing that's so that's the unique part about this machine, is that this is built with 10 millimeter aluminum extrusions here. And because, like I was saying, these are all 300 millimeters, and I don't want to cut any of the extrusions. I had to make the adjustments, I should say, dimensionally on my parts, so that when I build this assembly, these also fit in the same way in a press fit style, with provisions to support them through a screw on the side. You can see this one, it needs a screw on the side here, which has a screw, and it has a screw at the inside here supporting the verticals here, so it locks the part nice and rigid in a very true square 90-degree way. So it's a very nice little solid frame for using these skinny aluminum extrusions, and so I'm very happy with that, the way that came out. The hot end has to be built on top of extrusions that I'm waiting for. There's going to be 2 extrusions going this way right here, or maybe going sideways. It doesn't matter as long as there's a platform to support the hotbed properly, and so that it keeps things safe. You know, you want to install that as safely as possible. And you need I will have a heat brake plate. You know, we have heat brakes on the extruder here, from the nozzle to the aluminum heat sink. It's part of the extruder, and so we can do the same thing here with a heat brake on the bed. You know, just to break the heat from creeping into the support part. You want that heat on top, you know, where the build plate is going to be. This will probably have a glass plate on top, and because it's rigid, I don't have to worry about the weight here, as you do when you raise the table. Now you have a table that's got a little weight. You know, now you have to raise that weight. So that's not going to be an issue. The other thing that's very unique about this machine is that I did not want to use rails that are that you can purchase them off the shelf. Most people that build these machines, they build them with those linear rails that are typical. You know, those square blocks that have the recirculating ball bearings, and that adds, you know, another track here, another steel track that you need, and then you have the carriage. So it adds not only weight, but it takes up a lot of area or realty from the structure here, from the core XY structure. So I didn't want to have to minimize my travel XY distances beyond. You know, I didn't want to go too small here. With that, I mean, I could have used longer extrusions, but these come standard as 300 millimeters. You can buy them as a 1 meter length and then cut it, but I don't want to go through that process. I just wanted to buy. These are perfectly cut. They're clean. They're very nice parts, anodized. So I had to design this accordingly. So my linear rails are my own also. I have not seen people do linear rails like this. This is something that I came up after doing so many different variations of rails. I must have done about a dozen different ideas on how to make rails using the extrusion as the rail system themselves. So that's how I came up with that. These run on Teflon liners, and so this is a Teflon carriage, Teflon operated carriage. It's very, very smooth, and I have these little screws here, to adjust the tension on the Teflon liner. So in case it's a little bit loose, I can adjust for that. It's working beautifully. The same thing here on my Z-axis carriage is the same thing. And you can see these white plates right here are basically what's holding the liner inside this block here. On this one I have it at the bottom because this part on the top is already designed with a stop as part of but the part itself at the top, and it only needs a cover right here to access the liners from one side. On this one I designed it with both sides as the covers, and it looks pretty cool. You can see the machine from the side here. It's very, very clean. On my first Core XY machine, I did the Z-axis, the standard Core XY with a cube frame assembly. I did those with a belt-driven Z-axis. The only thing with belt-driven is that once you disconnect the motors, they lose their position, their true position, because they're not locked, and so the machine can get skewed, and then you have to readjust that every time. So that's the benefit of having the lead screws. The lead screws just lock it in place, and unless you move it physically, turn the screw, the whatever's connected to that, in this case the assembly, the XY assembly, is not gonna move. It's not gonna shift. So that's why I ended up using the lead screws here. I already did a test. I connected this machine to my cube. The X and Y motors connected it to the controller and ran some test runs here. It's kind of dry because no heat was applied to this, and it seemed to be working pretty flawlessly. I'm very, very happy with that. I worked very hard on this machine. It's taking me 2 weeks to complete this machine, almost pretty much with no sleep. Once my mind is set on some of these things, I tend to forget about hours, days. Sometimes I don't even sleep.